So I don't think I did a great job in lecture of explaining the technical side of dirty cow, so this is my attempt at rectifying that. To start off, I would like to simply go over the goal of dirty cow. The goal is actually quite simple. We want to write to read-only files. So these are files where we don't have permission to write to them, but we have permission to read. Diving straight in the code, we see an open call. We open a read-only file, and also notice the flag read-only. If we were to pass in a different flag, we would get a permission error. Next, let's take a look at mmap. Mmap maps a physical file on the disk to our virtual memory. Next, I would like to highlight two important flags in the mmap call. The first flag is prot_read. This flag describes the desired memory protection of the mapping, and it must not conflict with the open mode of the file. So the open mode of our file is read-only, so therefore our flag in mmap also has to be read-only. The other flag that I need to highlight is the map private flag. By having the map private flag set, we enable a private copy on write mapping. If we try to write to our map memory, instead of erroring out, this will instead copy the memory and allow us to write to that copy. So we can still make write calls, just not directly to the map region. So notice that changes we make to the new region after the copy and write won't actually be carried over to the original file. So this doesn't violate the permissions of the underlying file. But this is really clever. This means that our calls to write will still go through. Now let's take a look at pthreads. The important thing to note here is that pthreads share the same memory, are run in the same process, and that threads are scheduled by the operating system, so the code in them are executed at random. So although your code may be written in a certain order, they may not execute in that order. We will be taking advantage of this with our dirty cow exploit. Also, take notice of the two functions being run by our pthreads. These two functions will race against each other. I will expand on these two functions now. Now let's take a look at the first function being run by the pthread. This function first opens up a pseudo file called procself_mem. The self refers to this program, and mem stands for memory. And pseudo file means that this file doesn't actually exist on disk. It's generated by the kernel. This file contains the memory of our program. I will explain why we use procself_mem later. Now let's move on to the next flag. The next flag tells the kernel that we will either read or write to that memory. After that, we have two lines in a for loop. The else_seek moves us to the beginning of the map file, and the second line tries to write to that memory. But remember, this won't actually write to the map memory. It will create a private copy on write mapping. Recall that we set the map private flag in our mmap call. Now let's take a look at the other function. This function is repeatedly called madvise, and this stands for memory advise. And we are advising the kernel that we don't need our map region of memory. What does the kernel do? Remember that our map region of memory is mapped to an actual file on disk. If there are changes to that region of memory, the kernel will carry those changes over to the actual file. But of course, there shouldn't be, because that region of memory is marked as read-only. So instead, the kernel just discards that region of memory. Well, what happens if we try to access that region of memory again? Well, the kernel will just reload the mapping from disk. Now let's put it all together. This is the normal flow of execution. First, we make our mmap call, and that reads our read-only file into our virtual memory, like so. Next, our first function call calls else_seek, moving our file pointer to the beginning of the map region. After our else_seek call, we have our write call. However, remember that this region of memory is marked read-only, so normally we would get an error because we do not have permission to write to that memory. However, remember that we also have a map private flag. This means that instead of causing an error, a copy on write is triggered, creating a copy of the original mapping. This means that instead of writing to the original, the kernel lets us write to a private copy. This way, it respects the permissions of the original read-only mapping. That concludes the write thread, and now the madvise thread runs. Since there's no changes to the original memory, madvise causes the kernel to remove the mapping from memory. That is what should happen, and the cycle repeats. The mapping is brought back from the disk, and we repeat the exact same cycle. We have our else_seek, our write, our copy on write, our write to our copy, and then our madvise. So what exactly goes wrong? For that, we will have to look at the code more closely. But before that, let's take a look at what dirty cow actually looks like at a high level. Everything starts normally, the file is mapped into memory. lseek moves our pointer to the beginning of the map memory. Write happens, however, madvise executes during our write call. This somehow allows us to write to the original read-only memory. This is then carried over by the kernel to the file on disk. This is dirty cow. I'm sure you have many questions, so let us dive into the code and figure out why this happens. The first thing to understand is that write is not atomic. It is made up of multiple operations. This might look scary, but we'll simplify this, and this really isn't that hard to understand, so please stay and bear with me. Also keep in mind that pthreads are scheduled randomly by the kernel, so other threads and operations may execute anywhere during our write call. If madvise occurs at the right moment during our write call, it will confuse the kernel and allow us to write to read-only memory. This is the race condition and the purpose of racing two threads millions of times against each other. We want to achieve a specific ordering that confuses the kernel and gives us access to the original map memory of the file. First, let's take a look at the first two functions. This starts our write operation. It requests the memory that we want to write to. This call also sets a flag that tells the kernel what kind of access we want to the memory that we've requested. In this case, it's write access, and the flag is follow write. Before we move on, it's important to note that the kernel doesn't give us access to all of the memory we've requested at the same time. Instead, it gives us a page. What is a page? It's the smallest unit of memory that the kernel manages. So really, the kernel gives us access to memory a page at a time. As for the rest of these operations, their purpose is to get the page that we've requested and resolve any errors. Remember that we are writing to a read-only page. But since we have map private set in our original mmap call, we will not receive an error. Instead, we'll get a copied page that we can write to. This code does it for us. It handles a copy on write and returns to us a copied page that we can write to. I'm going to simplify this and only focus on the first three functions: get user pages, fault in pages, and also handle map memory fault. Again, this is a simplification, but get user pages starts it off. It tries to get the page we requested over and over again until it succeeds. Next, if there are any problems, for example, if the page we requested is read-only, but our follow flags contain follow write, fault in will be called and it will try to fault in the page. To do this, it will call handle map memory fault to resolve any errors for us. This is again a simplification, but for our purposes, we will assume that handle map memory fault will resolve any errors and return a valid page for us. Diving straight into the kernel, this is a snippet of the get user pages function. Notice that there is a loop. Simply put, get user pages will keep trying until it gets a valid page. Follow page mask tries to get the page, but since our requested access differs from the permissions of the page, it will return null. Because of this, this will lead us to fault in page to resolve this for us. Now we are in the fault in page function. Handle map memory fault will resolve the error by giving us a copy of the requested page, or a cowed page. However, notice at the end we modified the flags. Fault in pages actually removes the follow write flag from the follow flags. Why is that? Recall in our previous slide, if page permissions differ from the follow flags, follow page mask will return null, causing another call to fault in page. However, since we now have a cowed page, we remove the write flag to prevent an infinite loop. Now we are back in the get user pages function. Running the loop a second time, notice that our follow flag has follow read removed. Pay attention now, this is where the whole thing comes together. What if madvise were to run right now and drop the cowed page? If madvise drop the cowed page, follow mask will return null again, causing another call to fault in page, this time without the follow write flag. Now we're back in fault in page. This time, handle map memory fault doesn't see the write flag, so it returns the original page mapped to the original file on disk. Finally, we are back in get user pages for a final time. However, this time, the follow page map succeeds and returns the original page mapped to the file on disk. Any writes to this page will be reflected to the file on disk. This is dirty cow. We have successfully written to a read-only file. Lastly, I want to bring your attention to the function access remote VM, or access remote virtual memory, and explain why we open and write to proc self mem as promised. As stated before, this is a pseudo file, meaning it's generated by the kernel. It doesn't exist on disk. Therefore, the kernel must have direct access to our process's memory. This function allows the kernel to access our memory and generate the proc self mem pseudo file. Normally, this type of out-of-band memory access is used by debuggers. However, by writing to proc self mem, we are effectively piggybacking off the kernel's access to everything, even read-only files on disk. This is how we write the dirty bits back to the file on disk. That concludes my technical explanation of dirty cow. I did, however, gloss over some details, so I've linked a more complete explanation in the description below. Thank you for listening.